Let's take a look at Kepler's 3 laws. So, Kepler's 3 laws, and we'll make sense of them. Okay, the first law is the fact that satellites, moons, planets, they follow elliptical orbits. Now, a lot of the orbits are really, really close to a circle, and so we don't really care about the distinction, but his first law says that they actually do follow an elliptical orbit. Law 2, if you looked it up in a book, it would say something like sweep out equal area in equal time. And I kind of draw you a picture of what that means, but for us, I really want you to understand that that is talking about the conservation of angular momentum. And I wish it just said that in the law. But if you look it up in a book or you watched a YouTube video on it, it's going to say this sweep out equal area in equal time. And then the third law is going to be that the period is proportional to r cubed. And then we'll actually prove that. Again, this is period. And this is the radius of the orbit. Okay, let's draw a picture for this. Well, elliptical orbits would mean something like this. And so like pretend that's some planet, and then this is the sun. It's actually an elliptical orbit. The sweep out equal area in equal time is that if we take 1 week, and let's say that it goes from here to here in a week. Okay, it starts here and goes to here in 1 week. This is a certain area. Well, if we're way over here then, in 1 week, it's going to do the same thing. This red area and this red area are the same for the same time. So when it says sweep out equal area in equal time, it's talking about if this is 1 week of travel, this is 1 week of travel. And then we're going to look at the idea of conservation of angular momentum. So what we want to decide is the fact that when gravity is acting on the satellite rotating around, there's no net torque. Why is there no net torque? Gravity is always inward. And if gravity is always inward and the lever arm is straight that way, then there essentially is no perpendicular piece, right? The force is back and the lever arm is straight back, and so there's no perpendicular arm there, and so then there's no net torque. And gravity is not going to cause a net torque. And so what we can say is the angular momentum at one spot equals the angular momentum at another spot, because if there's no net torque, there can be no change in the angular momentum. And so that would mean then that mv1r1 must equal mv2r2. So when it's over here in the number 1 position versus the number 2 position, these quantities have to be the same, right? The mass doesn't matter. And so what does this say? This says when you're further away, you're moving slower. If you happen to be closer, meaning if R2 was smaller than R1, then you'd be moving faster. So over here, when you have a small r, you're moving fast, and over here, you're moving slow. And hopefully from the picture, you can see that over here, you're moving faster because you're zipping around, and then over here, you're moving really slow. And the corollary of that is this idea of sweeping out equal area in equal time, but really it's a conservation of angular momentum. So whether you're a satellite around the Earth, whether you're the Earth around the Sun, conservation of angular momentum is true. Why? Because gravity is the force, but it doesn't cause any torque. No net torque, no change in angular momentum. That means the angular momentum at 2 different spots have to be the same, which says this, right? This mvr is a constant, which means if we increase r, we decrease v, or if we decrease r, we must then increase the velocity. Okay, so that's Kepler's second law. And then this third law really just starts with a derivation, and you will have to derive this at some point. And start out with F equals ma. We know that the force acting on the satellite is the force of gravity, so gmm over r squared. we're going to assume again that it's a circle, even though we know truly it's an ellipse. It's going to be close enough for us that it's causing circular motion, at least at that point. It's really close to a circle. We can cancel the mass, which means that the mass of the satellite is completely independent of everything, right? Mass of the satellite, mass of the satellite. This m is like the mass of the planet. And we can solve this, right? We can also then get rid of that and get rid of that. And we can solve for v squared. So then v squared is going to be g m over r, okay? And then I can say, well, what do I know about the period? Well, the velocity is just the total distance. So what's the total distance traveled? Again, the total distance traveled is just the circumference. So that's some 2 pi r. And the time it takes to go around one time, well, that's how we define what the period is. If we square both sides, we're going to get v squared equals 4 pi squared r squared over t squared. And then let's go ahead and make a substitution. We know that v squared equals this. So we get g m over r equals 4 pi squared r squared t squared. And then if I move everything and I say then the t squared is equal to, it's going to make that r cubed, 4 pi squared over gm r cubed, and bingo. We have shown that the period is proportional to r cubed. And again, all I really did here was use the velocity was a distance divided by time, and F equals ma, and then for a I used v squared over r, and then I just did a little algebra. But this is Kepler's third law. And again, we derived it. You would have to do that on the test, and we're showing that the period is a function of r. Okay? Lots of times they'll do a graph of this. Let's say you have a whole bunch of satellites orbiting around some planet. You'd want to graph t squared versus r cubed. If you had all this data, then there's a satellite, there's a satellite, there's a satellite, there's a satellite, and you could show then that that's some linear relationship. And if you had this data, you could find the slope. And what's the slope equal to? Well, the slope's equal to that factor. And if you think about it, as long as you could observe the period, which is just the time it takes to go around, and the radius, meaning how far the satellite is from the center of the Earth or the Sun, then you could actually figure out the mass. Again, the whole point of this exercise would be to find the mass of the planet. And it would be the mass, the unknown mass of some planet. So if you knew like data about Jupiter's moons or Saturn's moons, you could take some data on them and get a really good idea of what the mass of the planet was. Okay? The other thing we want to look at is how much this connects all three of those things. So connecting the radius, the period, and the velocity. All three of those things are absolutely connected. All you have to do is tell me one thing. Not two, just one. You tell me the period. Well, once you know the period, then you know the radius, because they're a one-to-one relationship, right? You can't have a period and have this one's got a period of 7 days and have some different radius. It has the same radius as long as it's around the same planet. So if you tell me the period, I'll tell you the radius, but once you know the period and the radius, I'll tell you the velocity. What if I just told you the velocity of something? So I just knew the velocity of a satellite. Well, if you just knew the velocity of the satellite, you would know the radius, and once you knew the radius, you knew the period. Well, what if you just knew the radius, meaning you knew the distance the satellite, and really this is the radius of the Earth and this is the height. So if I just told you the height that the satellite needed to rotate, you could certainly figure out then r from that, but once you knew r, you knew the period, and once you knew the period, you know the velocity. Telling me any one of these things dictates everything. So in general, if you're NASA and you want a satellite and you want it to have a certain period, meaning you want it to rotate around the Earth in so many seconds or so many hours, I'll tell you exactly how high you need to put it and what speed it'll need to be going at. Or if you tell me you need a satellite at 10,000 meters above the Earth's surface, or I guess more probably better, like 100,000 meters above the Earth's surface, I'll tell you exactly what its period will be and the velocity necessary. So all of these things are connected, and again, you can go to Kepler's third law and show all of those connections.